prefetching can sometimes be useful to reduce or remove some cache misses. Whether it's applicable depends on the data structure. If we are traversing an array and we are at the index I, then we can easily compute the address of an element k items ahead. And if we know the address of the data that we want, we can use an instruction to prefetch that data. It means copying it from memory into a cache. And the disadvantage with prefetching is that we may copy it too early, so that it replaces some data that we still need in the cache, so that we get the cache miss, and then we may replace the prefetched data when we fetch the data that we actually wanted, and so we still have a cache miss for the data that was prefetched. So it's just a disadvantage. Another thing that makes data prefetching difficult is to figure out how many elements ahead that we should actually prefetch. It depends on the latency of fetching the data and of how much time, when we need it. So if we prefetch it too early, we can get more cache misses. If we prefetch it too late, we will not hide the latency. The latency is still there, but we try to hide it by doing something else when it's being copied to the cache. As I mentioned, we can do prefetching manually by inserting prefetch instructions. I will come to how that can be done with the GCC. But the compiler can also do that, and it has exactly the same problems, obviously, to decide what to prefetch and when. How many items ahead. But the compiler has even more problems because it doesn't know what is likely to result in a cache miss. So if there are just prefetch instructions for things that are already in the cache, then it's just a waste. There was a PhD study at Stanford which was done and evaluating compiler inserted prefetching, and the main work was about doing that for matrix codes, but they also as a minor part of the thesis to check what happens if you insert prefetches in some library codes such as memcopy, or the code that copies data from one place to another. And they found that it significantly reduces the performance. And the reason for that is that, for the programs that they evaluated, is that the data was in the cache sufficiently frequently, so there was just extra overhead of executing the prefetch instructions. And it's not only the prefetch instruction, it's the instructions that compute the address as well, of course. Okay, so doing the inserting prefetches in without considering whether it's likely to be beneficial is probably a bad idea. It's a bad idea in most cases. And this is for arrays, and for linked lists, for instance, or trees, it's even more complicated, because say we are at this node and we want to prefetch, maybe tens of nodes ahead, but that is practically impossible, because if we well, we must calculate the address, and we can only do that by dereferencing pointers. And what will happen is that dereferencing these pointers will typically result in cache misses. And it can, if we have been extremely lucky or skilled, prefetch items ahead, but it's very, very difficult. And a superscalar processor can prefetch to some extent, since it can reorder instructions and doesn't have to do them one at a time. But if we have a CPU which would prevent future accesses to the cache after the cache gets a cache miss, that is a blocking cache, then it is completely useless. So it must be a cache which can service multiple misses at the same time. But in general, it's just prefetching iterations ahead like this is very, very difficult. So it's much better to change the list to an array somehow, and I will soon explain how that can be done in some cases. I mean, it's not very difficult, but what has been evaluated. Okay, so the big problem with linked lists or trees is that the nodes have, there are different approaches to allocating the nodes, but one is to use new in C and Java to allocate one, in C++ and Java, to allocate one node at a time, and then they can be in any place in memory. So we can think of one node in one cache block if we are lucky, but the different nodes will live in different cache blocks, and we will get cache misses for every node. That's what we can expect in realistic situation, depending of course how frequently we reduce this list, obviously. If we instead allocate all the nodes for this list in one big malloc, and then create, we don't put the elements, well, they will be put in a list. So we have one array with the nodes, but we don't access it through the array, but we access them through the list. Then it is, we have next pointer, so this one may be pointing to that one, and to that one, and then maybe that one points to that one. So we can still traverse them in any order. Then it is more likely to have cache misses, to have hits in the cache, since, we have allocated the memory in one piece instead. So it's better than allocating using one new or malloc at a time. Okay, but it's not always we can do that due to the nature of a linked list that we don't know the size of, for instance. Okay. So what can we do? If we we can. I drew it again here. So say we have a tree, and I just draw this. If we will traverse this tree multiple times, and we don't change the structure of the tree, then we can create an array where we put pointers to the nodes in the traversal order, and then we can manually insert prefetches to the next node that we will visit. That can be done in some situations. For parallel machines, we have a very severe problem, namely that if we want to modify the data, then we should prefetch it in exclusive mode so that we get ownership of that data. But that means we invalidate other copies. Okay, so what will happen then? There is a risk that the other threads still want to read that data, and then they have got a cache miss. But without this prefetch in exclusive mode, they would not have had a cache miss. But still, it can be useful since it can remove the write penalty in a sequentially consistent machine. I mean, we don't have to wait for the ownership, and for if we have a relaxed memory model, then there will not be needed a separate message to get ownership. It's the same situation as when we had some object, and we can say we do it like this. Here, if this object that P points to is being used by different threads and in different caches, then it will migrate between different caches. Okay, and it's better to fetch the data with requesting ownership I mean, when we need it, so that we don't have to send a separate ownership request. That can sometimes be used using prefetching, so that we get the data in exclusive mode. There are, as far as I know, no machines with a load exclusive instruction. At least not yet. It was proposed in the mid 1990s, early 1990s, to have such a machine. And for codes which look like this, and it's quite common, it can improve performance quite significantly. Okay, so prefetching for exclusive mode is beneficial, since it can not only improve sequentially consistent program, I mean programs on a sequentially consistent machine, but it also can reduce the write traffic, so that the network has more place for other messages. So how can we do prefetch with GCC? There is this built-in function that takes an address, a parameter write, and a value saying to what extent this data is expected to have temporal locality. Okay, what that one is, it's quite obvious, but what this is whether we should modify, I mean get exclusive ownership at once or not. And this can have value 0 up to 3, and if it has value 0, it tells the compiler that, or the CPU we can say also, that this data will be used like once. And if it's 3, which is the indication of temporal locality, certain temporal locality, it should be put in the cache. Some CPUs, they have additional storage for temporary data. It's called sometimes called transient data. I mean, we can prefetch data in a transient mode so that it will just be temporary. And the purpose of doing that is to avoid replacing useful things from the cache. Okay, When we do a prefetch, what happens if this address is invalid? If we read an invalid address, it's undefined behavior, and the program will usually be terminated unless we have taken special precautions. But if we try to prefetch an invalid address, nothing happens. I mean, the CPU should just ignore it. Okay, but if we go here and we say that we want to prefetch a few iterations ahead, and okay, so we prefetch say Q next, then we get the segmentation fault. Since the program, when it calculates what to prefetch, I mean, then it can get the segmentation fault. So that must obviously be valid because, well, the compiler doesn't know it could have ignored it.